pi molecular orbital diagrams of benzene. So in the benzene, if we are observing 6 p orbitals in the pi system, will be produced 6 pi molecular orbitals. I mean 3 pi molecular orbitals are bonding molecular orbitals, whereas the other 3 are anti-bonding molecular orbitals. Like butadiene in 4, 2 are bonding, 2 are anti-bonding. In the benzene, in the total 6, 3 are bonding molecular orbital, 3 are anti-bonding molecular orbital. The lowest energy molecular orbital have 0 nodes, that is the pi 1. The phases of all p orbitals are aligned in same way. Here electrons are delocalized over the molecule, thus resulting in lowering of energy. You can observe here. This is the pi 1. So all the phases are aligned in the same direction. So are you observing? Is it visible to you?
Yes, ma'am.
So here there is no nodes, 0 nodes. It is the pi 1 having least energy due to 0 nodes. 0 nodes. Then next, the highest energy molecular orbitals has the maximum number of nodes. I mean pi 6 star I will show to you, as all the phases of p orbitals are aligned alternatively. No 2 adjacent p orbitals should have lobes with the same phase. But as benzene is a cyclic system, it fails n-1 rule. Therefore, benzene has only 3 nodal planes. If suppose 5 nodal planes or 6 p orbitals are there, if 5 nodal planes, if we are observing, I mean, there is no cyclic structure of benzene possibility. Hence, up to only 3 nodal planes only we can observe in this system, because benzene is the cyclic, right, and also aromatic. So we can easily draw an orbital where all the phases are alternate, but we cannot draw 6 nodal phases where the phases change. Having 3 nodal phases cut through the molecule at various points. This orbital has 0 overlap between adjacent p orbitals. Hence, electrons have the minimum possible delocalization and highest energy. See here, this one. This is the pi 6. Completely alternative. Completely alternative. But it is not possible like this. 6 nodes with 6 nodes, 6 nodal planes. So here also 5 star 6. So through this 1 nodal plane, through this 1 nodal plane, through this 1 nodal. 3 nodes, because these having to cut through nodes, through center of the it has to cut through center of the molecule. Then next, it is highly impossible to draw a cyclic pi system with 1 node, but we can draw a system with 1 nodal plane. 1 node is different, 1 nodal plane is different. Here there are 2 possibilities. One is through bond, that is pi 2. and the other is through atom, pi 3. These possess same energy. Here, this one node through bond. This is through bond. Clearly you can observe this is through bond, one nodal plane, but it is exactly cutting half through center. This is one is through node. One node is through atom, through this. This is one carbon atom. This is another carbon atom. So you can clearly observe. This is through atom. This is through bond. But these two having these two nodal planes having same energy, pi 2 and pi 3. But one is cutting through, one node is cutting through atom, another node is cutting through bond. So are you understanding? This is the bond between carbon-carbon. This is the bond between carbon-carbon. Here we are cutting. I mean, here nodes are changing, phases are changing. Here also. One node through bond, that is pi 2, we are representing here. One node through atom, through atoms, this is one atom, this is another atom. This is, we are representing as the pi 3 orbital. Next, the next level has two nodal phases, one through the bond and another through the atom, pi 4 and pi 5. These two. This is through bond. From this bond, from this bond. Okay. Then here through two nodes through atoms. This is through, actually, sorry, this has to be through this and through this atom. This is little wrong. You has to note it down. This carbon and this carbon will cut. Then this carbon and this carbon. Okay. So, two nodes through atoms, two nodes through bond. Two nodes through bond, two nodes through atoms. Pi 4, I mean, these are anti-bonding. Whenever nodes are more, nodal planes are more, I mean, they are they having high energy and also having high nodes. Highly, I mean, these are less stable. These are pi star 4 anti-bonding, pi star 5 anti-bonding. This is the pi 6 star. This is one nodal plane through here, one nodal plane through here, one nodal plane through here, one nodal plane through here. This is pi star 6. So here pi 4 and pi 5, pi 6 are anti-bonding pi molecular orbitals of benzene. Pi 1, pi 2, pi 3 are bonding pi molecular orbitals of benzene. These pi 1 having 0 node, pi 2 having 1 node through bond, pi 3 having 1 node through atom. So from the 6p orbitals, 1 electron is there from each orbital. Total 6 pi electrons are there in benzene. Among the 6 pi electrons, first 2 electrons enter into the pi 1 bonding orbital because it's having 0 nodes and least energy. next 4 electrons enter into the pi2 and pi3. These two are equal energy molecular orbitals bonding in the benzene. Pi1, pi2, pi3 molecular orbitals are bonding molecular orbital in benzene. Pi4, pi5, pi6 is the pi4, pi5 having 2 nodes, pi6 having 3 nodes. Hence, these are anti-bonding having more energy. Here, all 6 electrons from the 6 p orbitals came, or pi molecular orbitals came filled 2 electrons in pi1, 2 electrons in pi2, and 2 electrons in pi3. 6 are over here. These 3 are bonding pi molecular orbitals. Pi4, pi5, and pi6 are anti-bonding pi molecular orbitals. Benzene is more stable than hexatriene. Why? A cyclic pi system allows 2 ways to place 1 and 2 nodal planes. That is, one through bond and one through another one is the through atom. One through bond, one nodal plane is through bond, another nodal plane is through atom. Hence, benzene has second and third energy levels, each having 2 units with same energy as they are degenerate. Here, which molecular orbitals are orbitals having same energy, they are known as degenerate. Here, pi2 and pi3 having same energy, these two are degenerate. At the same time, here pi4 and pi5 are having same energy, these two are degenerate anti-bonding orbitals. These pi2 and pi3 are degenerate bonding orbitals. Pi4 and pi5 is the degenerate anti-bonding orbitals. Hence, benzene is more stable than hexatriene. So, you can reveal in the butadiene also, whenever we are explaining only, through nodes, we are cutting through bond only. There is no through atom. Here, 2 possibilities are there. One is through bond, another one is through atom. Hence, this is more stable. Benzene is more stable than concerned. Benzene pi system is more stable concerned hexatrienes. This is regarding molecular orbital diagram of the benzene. So you can easily understand pi1 is having 0 nodes, highly stable, less energy. Pi2 and pi3 are one node through bond, one node through atom. These two are degenerate bonding pi orbitals. And then pi4, pi5 having 2 nodes. Pi4 is through bond, pi5 is through atom. These two are also degenerate but having high energy. These are anti-bonding. Pi6, there is no pi7. Here we clearly explained. Each atom we may not cut here. In between, only pi star 6 only we can, 3 nodal planes we can cut here only. Hence, pi star 6 only we can observe. This is having 3 nodes, nodal planes. Hence, it's having highly unstable, it's having more energy, anti-bonding orbital. The highest energy molecular orbital has the maximum number of nodes as all the bases of p orbitals are aligned alternatively, completely alternatively. No two adjacent p orbitals should have lobes with same phase. But as benzene is a cyclic system, it fails n minus 1 rule. Therefore, benzene has only 3 nodal planes. Here we can easily draw. We saw here how all 3 nodal planes alternatively, if it can cut it through here. Okay, this is the pi molecular orbital energy, pi molecular orbital diagram of the benzene and its energy levels.